Hello, AP Chem. Welcome to Chapter 5, Gases. Zumdahl textbook, Chapter 5. This is the chapter that, if you remember from Chem 1, is the one with all the gas law equations in it. If we start with pressure, one of the gas characteristics that is caused by the molecules of the gas striking the surface of the container, we see that pressure um, is exerted by the atmosphere, which can be measured with a barometer. Torricelli invented the first mercury barometer in 1643. You can see a diagram of it down in the lower left-hand portion of the screen. If you have a pressure of a contained or confined gas, you can measure it with a manometer. Here we show the two types of manometers, the closed manometer, where there's a figure 1A here, where there's a vacuum on one side and the pressure of the gas pushes the mercury up the right side of the tube, and the height of the mercury in the tube is the pressure of the gas. We also have the open manometer, where instead of a vacuum you have atmospheric pressure. This allows us to measure pressures that are close to 1 atmosphere of pressure. The height difference of the mercury on the two sides of the glass tube will be the P sub H portion of the equation. And in this case, the pressure of the gas is stronger than the pressure of the atmosphere, so it's pH plus P atmosphere. If the left side had a higher mercury level, it would be P atmosphere minus pH. Pressure is measured in atmospheres. 1 atmosphere is the same as the pressure to push mercury up a tube 760 millimeters. So 760 millimeters of mercury equals an atmosphere. In honor of Torricelli, the inventor of the barometer, the millimeter of mercury unit has been named the torr, T-O-R-R, short for Torricelli. In physics, they would use units like pascals, which is newtons of force divided by meters squared, because pressure is force over area. So 1 atmosphere is 101,325 pascals. So pressure is the force exerted by the gas divided by the area over which it's exerted. And you can try interactive example 5.1, page 167, if you want to try a pressure problem. In 5.2 here, we look at 3 important gas laws developed in the 16 and 1700s and early 1800s. Boyle's law was the first one. Robert Boyle in the 1600s showed that the product of pressure times volume is always a constant for a fixed amount of gas at constant temperature. We see the graph of pressure and volume, and we see the inverse relationship over here on the top right. Another way of writing Boyle's law instead of PV equals constant is P1V1 equals P2V2, where 1 is the initial conditions and 2 are the final conditions. The gas laws are only completely obeyed by ideal gases. Real gases show some variation from ideal, and we'll talk about real gases later in this chapter. A couple of interactive examples on Boyle's law are 5.2 and 5.3. Jacques Charles came up with Charles's law, which is volume equals constant times temperature, which shows that volume varies directly if you have the Kelvin temperature as the y-axis. I'm sorry, the x-axis. So if you take volume on the y-axis and temperature on the x-axis, you'll get a direct relationship. If you do it in Celsius, you'll actually get um, a linear relationship which intersects with the x-axis at negative 273 degrees Celsius, or absolute zero. So in other words, the limit of volume shrinking with temperature is zero, so the lowest possible temperature gives you the lowest possible volume. Interactive example 5.4 is for Charles' law. Avogadro's law deals with the relationship between moles of gas and volume. The more moles of gas you put in a container at constant temperature and pressure, the bigger the volume will be. And so typically we see this when we blow up a balloon. The more gas we put in the balloon, the higher the volume of the balloon is. The balloon gets larger. Interactive example 5.5 talks about Avogadro's law. So mathematically, we have V equals K over P, and V equals BT and V equals AN, which combined gives us PV equals nRT. Over on the right, we show that there is a variation of PV equals nRT, which at high pressure, it doesn't really follow PV equals nRT. So this is only for ideal gas. At really high pressures, non-ideal conditions, this equation doesn't work well. R is called the universal gas constant, and its value is 0.08206 liter atmospheres per mole K. We call it an equation of state because it is an equation that describes the behavior of a gas, one of the states of matter. With this equation of state, any three properties can be used to find the fourth. So you can use PV and T to find moles, for instance, or you can use moles, volume, and pressure to find temperature. Now, the ideal gas law depends on it being at ideal conditions, which would be high temperature and low pressure. Interactive examples 5.6 through 5.10 illustrate the use of the ideal gas law, or the combined gas law, PV equals nRT, which is a combination of Boyle's, Charles, and Avogadro's law into a single gas law called the ideal gas law. The ideal gas law can be used to find moles, and so since you can find moles with the ideal gas law, you can use it in stoichiometry problems. So simply use the information in the problem to solve for moles, or use the moles that you get from the third step to solve for some other property like pressure or volume in the fourth and final step of an ECMS gas stoichiometry problem. One shortcut for gas stoichiometry is that if you are at standard temperature and pressure, which is 0 Celsius and 1 atmosphere, you can expect the volume of 1 mole of gas to be 22.42 liters. Call it the molar volume of gas at STP. So that can be a shortcut if the problem designates the conditions to be standard. You can also find the molar mass of a gas using this derivation from Pivnert. Basically, if you consider moles to be the mass of a gas divided by its molar mass, then P equals nRT over V, which is a version of Pivnert, can be rearranged to make P equals mRT over V molar mass. Then recognizing that mass over volume is density, you can get D equals M over V, or P equals dRT over molar mass. Rearrange that and solve for molar mass, you get molar mass equals dirt over P. So some interactive examples to help you with dealing with moles of gas are 5.11 through 5.14. Dalton's law of partial pressures comes up when we have mixtures of gases. Dalton in 1803, about the same time he was doing the atomic theory, said that the total pressure of a mixture of gases should be the pressure exerted by the individual particles, each individual gas. And so pressure total equals P1 plus P2 plus P3 plus dot dot dot. For a mixture of gases in a container, the total pressure exerted is the sum of the pressures that each gas would exert if it were alone. The pressure just adds each pressure for each gas together to get the total pressure. We call the individual gas pressures the partial pressures, and we say that the sum of the partial pressures equals the total pressure. Interactive example 5.15 deals with John Dalton's equation. One math problem that we didn't do anything with in Chem 1 is calculations of mole fractions. Mole fraction is the ratio of the number of moles of a given gas in a mixture to the total moles of gas in the mixture. Mole fraction can also be used with liquids in the same way, but we use the symbol X or chi to represent the mole fraction. So the mole fraction of the first component equals the moles of the first component divided by the total moles. We find that the moles are proportional to pressure for both the individual components and for the total, so this could also be found using pressure of the first gas, the partial pressure of the first gas divided by the total pressure. Interactive examples 5, 16, and 17 let you deal with mole fraction. Probably the most common way we use Dalton's law of partial pressure is to make a correction when we collect a gas over water. When you collect a gas over water, your gas is always mixed with water vapor. So as a mixture of gases, the total pressure of the gases is equal to the pressure of the water vapor plus the pressure of the gas. Water vapor pressures for different temperatures can be looked up in a chart. And so basically you take the pressure of the collected gas, subtract off the water vapor pressure, and that gives you the pressure of the gas if it were dry. Interactive example 5.18. So our kinetic molecular theory of gases explains why gases behave the way they do. Laws can be explained by theories, and the theory for gases is the kinetic molecular theory, which if you look at the important words in that title, kinetic is motion, molecular is particles, and so kinetic molecular theory of gases is based on the particles of gas moving. The four postulates of the KMT are that the particles in a gas are so small compared with the distance between them that the volume of the individual particles can assume to be negligible or zero. The particles, number two, are always in constant motion, and the collisions of these particles with the walls of the container are the reason why a gas exerts pressure. The particles are assumed to exert no forces on each other. We do realize that they have elastic collisions with each other, but they are assumed not to interact in ways that cause attractions or repulsions. Finally, the average kinetic energy of the collection of gases is assumed to be directly proportional to the Kelvin temperature of the gas. So these postulates explain ideal gas behavior, but they don't hold for a real gas. Real gases have attractive forces, and they also have molecular volumes that are not zero. So if we take the kinetic molecular theory, we can explain the various gas laws. We can say, okay, for Boyle's law, decreasing the volume increases the number of collisions of the gas molecules with the walls of the container, so pressure goes up. When we look at the pressure-temperature relationship, we say that as temperature increases, the molecules colliding with the walls of the container have more force of collision, and so the pressure goes up. Charles' law can be explained as the volume goes up because as temperature increases, molecule collisions with the walls push the flexible walls of the container outward in order to maintain the same pressure. Avogadro's law, the volume is proportional to the number of moles of gas. When more moles of gas are put into a flexible container at constant pressure, the gas molecules collisions will push the walls farther out. So in all, we can explain the various laws using the kinetic molecular theory. Zumdahl does a very interesting derivation of the ideal gas law, PV equals nRT, for those that like physics and using physics equations. He actually derives the form of the Pivnert law using the physics of moving particles colliding with the walls of the container. And so it's a very interesting derivation that he does, and it's in Appendix 2 of the textbook. Important to realize that this fourth postulate, the average kinetic energy of gas particles, is directly proportional to Kelvin temperature. What we mean by temperature is a measure of the average kinetic energy of the particles in a sample. In other words, as temperature rises, the particles are going to be moving faster and have more kinetic energy. For an ideal gas, the average kinetic energy should be 3/2 RT. The particles of gas have random motion, and as a result, they have many collisions per second, and these change the directions and velocities of the molecules, but despite the randomness of the motion, the average kinetic energy or energy of motion of the particles, which can be calculated in physics, Ke equals 1/2 mv squared, is proportional to the temperature. Now, when discussing average velocities, since kinetic energy and temperature are really proportional to velocity squared, it's actually more appropriate to do your discussion in root mean square velocity, or URMS, which is the square root of the average of the squares of the velocities. So it's a little more complicated than just the average velocity. The root mean square velocity is equal to the square root of 3RT over the molar mass of the gas. For this equation, you should use R equal 8.3145 joules per mole second, which is another version of R using different units. And your molar mass should be given in kilograms. So for example, instead of 32 grams per mole for O2, you would say 0.032 kilograms per mole, since kilograms is one of the units that are combined to make the joule. If you use your units appropriately here for URMS, you will actually get the root mean square velocity in meters per second. So you can try one of those in interactive example 5.19. The range or distribution of the velocities of gas molecules, because not every gas molecule in a sample has exactly the same velocity, the range or distribution of the velocities in a gas sample can be illustrated using a Maxwell-Boltzmann graph. And below we see two graphs of the maximum Maxwell-Boltzmann distribution. The first one shows that as temperature goes up, that the average speed of the molecules goes up. Also, you see that they spread out more as temperature goes up. So at 100 K, the average is lower, and the gas speeds are much more concentrated in the low velocity. At 1000 Kelvin, the average has increased, but we also see that the distribution is much wider and more spread out. We see a similar effect for gases at the same temperature based on molar mass. The heavier molecules have, because they have a higher mass, they have a lower velocity. Because they have a lower velocity, their velocities are more concentrated in the low end of the spectrum here. So a gas like xenon has basically appears to look like a low temperature gas, when in fact it could be just because the gas is heavy, it moves slow, not because it's at a low temperature. And then the blue in the graph here, which would be helium, is shown to have a very high speed in meters per second on average, and also to have speeds that are much more widely distributed or more spread out. When we talk about the movement of gases, we can talk about two things that gases do. One is that gases diffuse or mix or spread out, and that's just due to the random motion of the particles of the gas. Another one is that if you have a tiny hole, like a hole in a hole in a tire, like a lawnmower tire or a car tire, the gas escapes through that tiny hole through a process called effusion. Graham developed a mathematical law that shows the rate of effusion. So this would be the rate at which a gas can escape through a tiny hole. And it allows us to actually get a peek at the speeds of molecules and a little in comparison of two gases based on their molar masses. And the equation shows that rate of the first gas A divided by the rate of the second gas B is the square root of the molar mass B over the molar mass A. And so we see this is an inverse relationship, but it's a relationship based on the square root of the molar mass. Interactive example 5.20, page 197, gives you a chance to practice Graham's law of effusion. Diffusion actually, you can't use Graham's law for diffusion because it's slightly more complicated than effusion is, but you would see that a lighter gas would diffuse faster. For example, ammonia NH3, which weighs 17 grams per mole, will diffuse faster than HCl, which weighs 36.5 grams per mole. This can be shown by putting cotton wool with ammonia soaked in it on one end of a glass tube and HCl soaked cotton wool on another end. The gases will actually travel toward the center, but they will meet and form the white cloud of ammonium chloride solid closer to the HCl side. And that's because HCl moves more slowly than NH3. Even though the particles are moving around 450 to 600 meters per second, it will actually take a few minutes before you will see the white cloud. And that's because, as illustrated by the lower right-hand corner, the particles do not just move from left to right or right to left. They bounce around off of other particles, changing direction frequently. And so it takes them quite a while to actually move from one side of the glass tube toward the other. Okay, as promised, we were going to talk about real gases and how they vary from ideal gases. No gas is in fact exactly ideal, although some act more ideal than others, and at certain conditions they will act more ideal. So the assumption that PV equals nRT is for particles that have no attractive forces and consist of infinitely small molecules. Of course, those don't really exist. At high pressures and low temperatures, you can't really assume no attractive forces and infinitely small molecules, because at high pressures and low temperatures you are crowding molecules very close together, and so their molecular volumes become a large percentage of the volume of the container, and attractive forces are more likely to form under those conditions. Plots of PV over nRT, if you think about it, PV over nRT should equal 1 if the ideal gas law is being followed. Should be a straight line with y equal 1. However, as we see on these graphs, you do have some variation from PV over nRT equaling 1. And these differences are most pronounced at very high pressures like 200, 400, 600, and 800 atmospheres. So the left two gases are showing the variation of PV equals nRT for different gases. You do see that some gases vary more than others, and generally that's because they have larger molecules and more attractive forces than others. But we also see that the variations from ideal behavior are less at higher temperatures. So we see down here in the third graph that at 873 Kelvin, the graph actually does stay closer to PV over nRT equaling 1 than it does at lower temperatures. So to summarize, you want your temperature to be high and your pressure to be low for PV equals nRT to give good results. If you don't want to have any error, or at least have less error, the van der Waals equation is available. It says that P plus A n squared over V squared times the quantity V minus NB is equal to nRT. So this has a couple of extra correction factors. The A factor is for attractive forces, and the B factor is for the molecule volume. And so by accounting for those non-ideal properties, you can actually get a more exact equation, which will give you better results at low temperatures and high pressures. In looking at that in a little more detail here, what are the characteristics that cause molecules to vary from ideal behavior? Typically, the graph dips below y equals 1 and then rises to above 1 if you look at those graphs on the previous slide. And that's because at first, crowding the molecules together actually favors increased attractions. Increased attractions pull the molecules toward the middle, lowering the volume and lowering the pressure. And as a result, the ratio PV over nRT becomes less than 1. However, when molecules are so close that they begin to get nuclear repulsions, you can't get molecules too close or they begin to repel. The repulsions actually increase the pressure and push the molecules apart, trying to increase the pressure and the volume. And so as that, when that begins to happen, the ratio PV over nRT actually goes up. If you look at the four gases, hydrogen, nitrogen, methane, and carbon dioxide, because the smaller ones have less molecular volume and less attractive forces, you see H2 having the least variation, N2 having next, CH4 next, and CO2 the most variations from ideal behavior. Finally, and I'm just going to hit the high points on 5.10, Chemistry in the Atmosphere. I encourage you to read some of the discussion there in Zumdahl, because he goes into some detail into the various reactions that can occur that cause pollution in the atmosphere. I think it's important that you know that there are four important gases in the atmosphere: nitrogen, oxygen, water vapor, and carbon dioxide. And that the chemistry of the lower atmosphere is dominated by the oxygen-carbon dioxide balance. Photosynthesis makes oxygen, and cellular respiration uses up oxygen and makes carbon dioxide. One issue is that burning fossil fuels upsets this balance by adding carbon dioxide to the atmosphere. So that's been in the news a lot lately with people's carbon footprint and carbon dioxide contributing to the greenhouse gas as a greenhouse gas to the greenhouse effect and global temperatures. Nitrogen and oxygen, which are in the atmosphere as the two main components, when they are drawn into an internal combustion engine, the high temperatures of the internal combustion engine can actually cause the oxygen double bond and the nitrogen triple bond to be broken, resulting in nitrogen oxides being able to form and come out the tailpipe of your car. Once it gets into the atmosphere, there's a variety of reactions that can occur, resulting in something called photochemical smog. Another problem with air pollution is the sulfur that is found in some versions of coal. Illinois coal has a lot of sulfur in it. When you burn the coal in a power plant, you produce sulfur oxides. When the sulfur oxides get into the atmosphere, they react with the water to make either sulfurous or sulfuric acid, and as a result, you get acid rain resulting. It is possible to improve this problem by scrubbing the smokestacks or adding limestone to the combustion chamber, which, as Zumdahl shows in the chapter, uh, can help to take the sulfur oxides out of the reaction. Something I don't know if Zumdahl goes into this or not, but there's also some chemistry in the ozone layer, which is up around the stratosphere, and the ozone layer is a protective layer that helps absorb ultraviolet light from the sun, protecting us from skin cancer and from the harmful rays of ultraviolet light. However, one contribution that is possible is chlorine atoms in the upper atmosphere can catalyze the decomposition of ozone. And chlorine atoms are usually formed from CFCs leaking into the atmosphere. So as a result, CFCs have been phased out in the 1980s and 90s in favor of less harmful refrigerants to use in our refrigerators and air conditioning. So thank you for listening, and that is Chapter 5, Gases.